I welcome you to a new video. Today we will implement the control unit, which is this unit here. This is like the heart of the microcontroller because here we decide what we do in each clock cycle. So one can see here we have inside this model and finite state machine, and this finite state machine we will implement as a milli finite state machine because we already used a Moore finite state machine here in the GPIO model and here also in the bus model in the test bench when you remember, and therefore we want to use here a milli finite state machine. And as you can see here, we have here different states. We have on one hand the instruction fetch, and I want to go here through this step. So first I want to explain what the instruction fetch is. In the instruction fetch, as it says, we fetch the instructions. So we get here from the program counter an address, and this address we fetch and then forward it here to the ROM model or to some other models, maybe to the RAM. It depends what the program counter value is. Here and we only have a ROM, so this program counter will always point to the ROM model. And then, as we have seen the last time, one clock cycle later, and we receive the data which is stored inside this ROM model. And then we are already in the next state, and this is the instruction decode. So we get here some data from the ROM model, and then we analyze this data and configure the other models correctly according to the instruction we get here in the data. And how an instruction could look like, we see here. So here, for example, we have an addition instruction. Here we have the operation code so that the ALU knows what to do. Does the ALU has to subtract or add or do something else? Therefore, we have here an operation code, and this operation code we can take out of this data signal and forward it here to the arithmetic unit. We also have here some destination signals and some source signals. So here we could forward the source signals. That means, for example, when we have an add instruction, which two registers we see here, and we come to that afterwards, what the CPU registers are, but we have here 8 registers, and maybe we want to add in an instruction 2 of these registers. So we need to define which 2 registers we want to add, and then we forward it here to the operation 1 and operation 2. And we also need a destination where we want to save afterwards this result, maybe here to register 0. And therefore that's everything we define here in the instruction decode. So we look inside here the data, what do we actually want to do inside this instruction. And then we get finally to the instruction execute state, and there we set, for example, the enable to 1. So we know, okay, the arithmetic unit knows, okay, now I can do the addition. Here in the operation 1, operand 1 and operand 2 have the right values, and we enable, for example, here the result so that the result can be saved inside this register. And that's already it for the simple commands, but there are also more difficult ones. For example, when we want to read here something from a register, maybe from register 0, and store this, for example, inside the GPIO model, we do exactly the same as before. So we first load here, the program counter increases maybe, and then we load here our instruction, then we decode it, and we see, okay, we want to make a memory access. That means we want to read here something and write it maybe to this GPIO file. So we set the destination correctly and maybe source 1 correctly. So in the destination, for example, is the address. So we inside this register is not a value but an address, for example the address of this GPIO model here, and we have the data we want to write, which is maybe the LED is lit or not lit. Therefore in the instruction execute we read here the data and the address. So we provided here the destination and the source. So we already have here some signal 1 clock cycle later. Then we are able to read this, and in the memory access we will forward this. So we will set here the address, the data and the write enable, and then actually write it to the GPIO model. And when we want to read something or write something here in this register, for example register 1, what we do then is nearly the same as when we make a memory access, but we also get here, for example, the address, not the data. And then in the memory access we write here the address, and 1 clock cycle later we get here the data. And then when we get the data, we are in the register write back statement. So we can enable the data here and insert here the data and the destination, and therefore write in this statement the value, for example, from the GPIO 0 model here inside a certain register, so that we know, okay, the LED is lit or not. I think the easiest way to understand it is afterwards when we really implement some ROM code here. But first of all, what I want to do in this tutorial is to implement this control unit. This could be quite complex, but we try it now, and I hope you can follow along this video. So what we will first want to do is to add a new source, add or create design source, yes. We create here a new file and we name it CPU Control, yes. And we want to have it inside the MCU lib. That's also okay. Okay, yes. And now we should see that we have here a new model, yeah, the CPU Control model. And what I do first is, as an example, I copy here the ROM code. So we already have here inside the ROM the correct libraries, so that I do not have to type it again. And we also can name it CPU Control and rename here the other things. And now we already have the general structure for our model. And when we have a look again on the schematic, we see here we have many inputs and outputs. So let's implement them. We have here a bus in and we have a bus out, which are actually directly connected with this model. And then we have here 6 other signals from the CPU 2, from the arithmetic unit 2, and from the program counter 2. That's quite a lot, but first start with the bus in signal. Yeah, and then actually we also have a clock and a reset. So let's create first the reset. This is also an input of the type STD logic. And then we can start with the bus in and bus out. And the bus in, when we have a look again, the schematic, the bus in is a bus to CPU record. So this is type bus to CPU, when I'm correct. And I think we actually have this already implemented in the libraries. We can have a look again. Let's search for CPU. Type bus to CPU. Yeah, exactly. We already defined that the last time. So that's fine. And we have also an out signal, which is CPU to bus. And then we have some more signals, like the register in, which is an input of the type register, output of the type controller unit to register. And then we have an output of the type control unit to program counter. And the same for the arithmetic unit. We have an input, which is an in type arithmetic unit to control unit, and an output, which is of the type control unit to arithmetic unit. And as we can see here, some records that are not defined at the moment. So first of all, we have to define them in our MCU package. For that, I make a new section and I say that it's a control unit. As we saw before, we need to define on one hand the register record. And when we look again on the schematic, we have the different types. We have data and address for the register to control, and for the control to register, data, source 1, source 2, destination, enable result, and enable data. So let's go back to Vivado, and actually we can copy here something, because for the bus we had nearly the same. So let's copy that down here. And actually here we have to say end record. And now we have the control unit to the register. And we have the register to the control unit. And as we saw before, we have here from the register to the control unit the data, which is actually correct, but we also have an address. So let's change that here. And this is actually the address width. And here we have source 1, which is also an STD logic vector. And as we saw before in this table, this is also has also a certain size. And let's say we have a register ID width. And this register ID width, when we look at the schematic, we have 8 registers. And to give a unique ID to each register, we need 3 bits. So let's say this has a register ID word width here as an input, and the same we have for source 2 and the destination, and the register ID word width we saw before in document I showed you that this has the value of 3. So we have here source 2 and also the destination. So we have a constant register ID word width, which is of the type natural, with the range 1 to, let's say, data width, and is equal to 3 as we saw before. And we see here all the errors are gone, but here we have some more signals like the data, which we can actually copy from there. And then the enable result, which is of the type STD logic, and the enable data, which is also of the type STD logic. Then we have the same for the program counter. So let's copy that. We have control unit to program counter, and the program counter to the control unit. And here we have an enable and mode and an address. And the address, we know here address width. These signals here we do not need, and this, the enable, is of the type STD logic. And for the mode we define a new type named type program counter mode. So let's define it. So type program counter mode is linear, absolute jump, and real offset. Here we actually have to write a T. And now, yeah, this is also correct. And we can also do the program counter to control unit, which has the program counter and then exception. And the program counter has actually the address width, because we want to overgive there an address to read the instruction from the ROM. And the exception, here we can define actually a new type address exception. And this type address exception is no error, linear error, and real error. Yeah, and then we actually have our last two type records, which is from the control unit to the arithmetic logic unit. So let's do that here. And here we have the operation, the immediate, and the enable. And as you can imagine, the enable is an STD logic, and the other two types are STD logic vectors. And when we have again a look on this table here, we see here we have an operation code width of 5 bits. So let's define that. So we use here operation code width, which is a constant -1 down to 0. And here in the immediate, we use also an STD logic vector. And the immediate value we saw also here, not in this one, but in this one, that this has a size of 8. So let's define also here constant and implement it like this. So let's say this is immediate operand word width -1 down to 0. And here we forgot semicolons. Yeah, and this two we have to define. So we can say constant operation code width is of the type natural in the range 1 to, let's say, data width, and is equal to, we said 5. And we also have another constant, immediate operand word width, which is also of the type natural, range 1 to, let's say, also data width, and this is actually equal to 8, we saw before in the table. And something we haven't considered here, and for the ALU, we do not need the whole operation code width, but only a few operations. So we could say this does not have to be 5 bits, but for example only 4. So let's define here a new constant. So here ALU operation word width, and we can say this is 4, because the first bit we can say this is only for other instructions like memory access or memory write back. So let's change this here, operation address width. And then down here the only thing is the flag. The flag is when we have an error, maybe in the arithmetic unit, for example an overflow or a carry, And then we can raise a flag, and for that we also define here a new type, and this could be type flag array. And this type we also have to define first. So we have a new type flag array is set, n, c, o, and set, let's say here flags, and type t flag array is array of type flags of std logic. So each of them could be 1 or 0. When we have an overflow, the O would be 1. If we have a carry, the carry would be 1, and so on. So yeah, that's already it here from the entity. So we can go again to our CPU control, and we see here everything works perfectly fine. And now we can actually go into our architecture and start our finite state machine, or a part of the finite state machine. So we define the states. Type state is, and as you maybe remember, we have an state instruction fetch, stage instruction decode, stage instruction execute, stage memory access, and stage register write back. And for the melee finite state machine, we need also here the next state and the current state, which are of the type state. And yeah, that's already it. So we can define here some registers. So for example, the instruction. So let's create here a register of the type std logic vector. And as we've seen before, the instruction has an of the data width. So let's say here data width -1 down to 0. Then we have a signal instruction enable of the type std logic, and signal with the operation code of the type natural, range 0 to 2 to the power of the operation code width -1. So, and here we can use the operation code width, because we have so many different operation codes we can actually have, because we have 5 bits. Then a register for enabling the result, which is of the type std logic, and a register for enabling the data, which is also of the type std logic. And then we can actually do some direct assignments. For example, the pass out dot data is equal to the register in dot data, and the operation code is equal to the corresponding bits in the instruction register. So let's say to integer unsigned, and then we have the instruction register, and there the corresponding bits, which are from data with -1 down to data with minus operation code width, and the alu out dot operation, is just 1 bit less than before. So it is the instruction register data with -1 minus we could write 1, but what is better is operation code width minus ALU operation word width down to data width minus operation code width, and the ALU out we actually have to write correctly, otherwise it will not work. Yeah, and the ALU out dot immediate is equal to instruction register, and let's define here a new constant, input output word width -1 down to 0, and we saw that the immediate has a width of 8. So let's define this constant in the MCU package. We already defined it here. Yeah, that's perfectly fine. So yeah, that already works. Then we have the register output the dot destination, which are the instruction register bits from 10 down to 0. We can also have a look again on the table. So we are here 10 down to 8. Sorry, 8. Yeah, that's clear. And then we have also source 1 and source 2. So source 1 and source 2. And this is actually true when the operation code is larger or equal 12 and operation code is smaller or equal than 15. Else, then it is namely the instruction register 7 down to 5. And source I have to write correct here. Yeah. And here the source 2, when we look again, here we have from 4 down to 2. So let's say that here 4 down to 2. And then for the jumps, program counter output dot address is equal to instruction register address with -1 down to 0. And register out dot enable result is equal to register enable result. And that's already it. So we can start now with a process. So let's create first the register block interface. Processes register block interface is a process which is sensitive on the clock. Then you can say in process begin if rising edge clock, then register out that enable data is equal to register enable data, and register out of data is equal to pass in dot data. And then we can make an end if, and this process is already finished. Then we want to make a process which stores the instruction. So process instruction register of the type process, which is sensitive to the clock. End process. We can say begin if rising edge clock, then and if we want to store the instruction, if instruction enable is equal to 1, then and if instruction register is equal to data in. So we look that always in the instruction fetch that then the instruction register is written here. So we make sure that then the instruction enable is 1. And here actually it's bus in the data. Yeah, so we always want to make sure that when the instruction decode, when we are in the instruction decode state, that this instruction enable is set to 1. So now we are already able to implement our finite state machine. So process finite state machine is a process which is sensitive to the current state on the operation code, on the arithmetic unit input, on the register input, and the program counter input. Then we can say end process. Here we could say begin. And now we could make some default assignment. So we can say the next state is equal to the current state. And the bus out dot write enable is equal to 0. And then we can copy that. Is equal to 0 as well as the instruction enable. Register enable result. Register enable data. Alu out dot enable. And the program counter out dot enable. And the program counter out dot mode we can set to linear, and the bus out dot address we can set everywhere to 1. So let's say address is equal to 1. And now we can begin a case statement. Case current state is when state instruction fetch, then if program counter in dot exception is equal to no error, then and if bus out dot address is equal to program counter input dot program counter, and then we could say the next state is equal to the current state. When state instruction decode, then instruction enable is equal to 1. So here we store then the bus in data. So this is set to 1, and then we store equal to 1. So in instruction decode, we store here the instruction in the instruction register. And the next state is equal to the current state. When state instruction execute, then now we have to look what to do on the different operation codes. And actually here I have not to say next state, but state instruction decode, and here state instruction execute. Here I have to look on the operation code. So if opcode is smaller equal 7, or opcode is larger equal 12, and opcode is smaller equal 15, then program counter out.enable is equal to 1, and the register enable result is equal to 1, so that we can write the result from the ALU inside the correct destination register in the register model. And the ALU out.enable we also set to 1, so that the ALU outputs something. And then we can say the next state is equal to state instruction fetch. And here I forgot the semicolon. Then we can make an else if opcode is equal to 16, or opcode is equal to 17, then maybe you remember these are the load store instructions. Program counter out.enable is equal to 1, and the next state is the state memory access. And now we also have more complicated commands like a jump. So we could say the jump command is that address before. Then you can say again program counter enable is equal to 1, and the next state is state instruction fetch, and program counter out.mode is equal to absolute jump. Now we can make the branches, and let's say the branches are from 25 to 29. So opcode is larger equal 25, and opcode is smaller equal 29, then again next state is state instruction fetch, and program counter enable is equal to 1. And now in the normal case, if operation code is equal to 25 and ALU underscore in dot flag set is equal to 0, so no flag is set, then and if program counter out.mode is equal to rel underscore offset. So this is actually a branch if not equal 0. Then we could make a branch if greater or equal. So therefore we could say if operation code is 26 and alu in flag carry and alu in flag n is equal to 0, or alu underscore in dot flag set is equal to 1. Then we can do a branch if less than. So let's copy this. Let's say 27, and this we can delete. Is equal to 1. Then do that. And if operation code is 28 and flag C, so branch if carry set, and then the last one, 29, branch if overflow set, and then we could do an else, and there we could do again these two statements, and then the end if, and then the next when state memory access. Then we want to do the following: if the operation code is equal to 16, then we know it's a load instruction, and we want to have also the last step, so we can say next state is equal to state register write back, and else pass out dot write enable is equal to 1, and the next state is equal to the state instruction fetch. Then and if, and the pass out dot address we can set in both cases to the register in dot data, register in dot address. Then when state register write back, we want to say register enable data is equal to 1, and the next state is state instruction fetch, and when others, then the next state is state instruction fetch. Then we can end case, and the end process we have already there. And then we need a last process for the finite state machine. So process finite state machine sequential process, and this one is now sensitive to the clock. The other was not sensitive to the clock. Then we can say begin, then end process, and then as always, this we could also make sensitive to the reset, so that we also use the reset. And then we can say if reset is equal to 1, then current state is state instruction fetch, else if rising edge clock, then current state is next state, and if, and process. Yeah, and that was already it. I hope we have no error inside this model. I will not write a test bench because I think it would take too long and it would not be very interesting. But what I can also do is to define the operation code here in the MCU package. So let's do that also here. So let's say type instruction is, and now here we could define all types like add, subtract, and so on. I will write here some down. What I mean I will explain in another video, for example when we implement the ALU. Yeah, and now we can create the subtype from T ALU instruction is of the type T instruction, range it to set immediate high. Then we can make here range, I have to write correctly, type T operation code is array T instruction of std logic vector, and now the operation code width -1 down to 0. Yeah, and here we have to write brackets, otherwise it is not correct. And then we can make a new constant, operation code of the type operation code is equal to, and now we can define the operations. So we could say add is equal to 5 zeros, and subtract is, for example, equal to 4 zeros and 1, and so on. So Andy is equal to 4 zeros, 1 0, and Ori is equal to this. Yeah, and then we could say others are equal to others, everywhere just the one. And that's already it. Yeah, I hope you saw how we implemented the control unit, how we implemented this one, and I hope you also understand a little bit how this control unit works and yeah, how this whole microcontroller operates. I think you understand it also a little bit more once we have implemented the LU, and these two models are very simple. So for these two models, we do not need much of effort. One more big thing we have to do is only the LU. Yeah, this was it, and I hope I see you in the next video.